Section 4, the pH scale. So we're going to talk about the different ways of assessing whether something's an acid or a base and how to calculate the pH, which is the acidity level. So pH is defined as the negative log of the hydronium concentration. This will help answer everything. P equals negative log of whatever. That's the answer to everything whenever you look at something like this. So what does that mean? pH, remember P equals negative log. So the negative log of H, which is the hydronium concentration. So if it says POH, you're looking for the negative log of the hydronium concentration. P whatever, negative log of whatever. PX, negative log of X concentration, okay? That's what P means. So pH, negative log of the hydronium concentration. Okay, just looking at this, these are just a few calculations, trying to find it. Yeah. Okay, that's just basically all plugging into the formula for pH. So you find the concentration, the molarity of the H plus ions, and you plug that into the negative log of that concentration. That's how you find the pH. So negative log of the hydronium ion concentration finds the pH. Same thing can be said for whatever concentration you're using. Acids are anything that's less than 7 on the pH scale. Neutral is 7. Neutral, generally, the only thing we're going to talk about is water. Bases are anything higher than 7, and it goes from a range of about 0 to about 14. It's weird to think that as you got to remember that if you're increasing in numbers, so let's say you're going from 2 to 4, you're getting less acidic. And if you're going down in numbers, you're getting more acidic. So, and it goes the opposite way for bases. If you're going up, you're getting more basic. If you're going down, you're getting less basic. So just know that if I were to draw a number line here of 0 and 14, that this would be acids, bases, and then right in the middle would be neutral. Oh, it sometimes helps to draw that out if you can't visualize that. Okay. This is talking about the concentrations for hydroxide and hydrogen. Remember that these concentrations can be used in order to find the pH. So the concentration, if it's greater than 1.0 times 10 to the negative 7th, it's going to come out with a pH that's less than 7. It's generally something that has a high concentration of hydroxide ions. It's going to be more acidic. And think about that. We were talking before that acids are things that increase the hydrogen ion concentrations or the hydronium ion concentrations. And then things that have a higher concentration of hydroxide, so OH minus ions, are going to be things that are more basic. Remember, the Arrhenius theory says that bases are things that increase the hydroxide concentration in water. Okay. Another important thing to remember is that, and if you don't know this now, this is very important, pH plus POH equals 14. It's on your reference table, should be pretty self-explanatory. If you ever need to use that, just plug it into that formula. That all has to do with the concentrations adding up to 1 times 10 to the negative 14. I don't know if we get to that. I think we actually might, yeah. So this is what I was talking about before, where the P just means negative log. So POH, negative log of OH. POH, negative log of OH. Again, pH plus POH equals 14 at 25 degrees Celsius. They're not going to give you another temperature and try and trick you like that. They just won't do that. KW is the concentration of water. So remember, water has a pH of 7, so it's neutral. If it's neutral, it has an equal concentration of hydrogen ions and hydroxide ions. So when you take the negative log of the hydroxide ion plus the negative log of the hydronium ion, you get the negative log of Kw, because remember Kw is that. So then it can be restated as pH plus POH equals pKw, but pKw equals 14, so that's how you get to this equation. pH plus POH equals 14. Just in case you were wondering how to derive that. These are just looking at the scales. I don't like how they have this in reverse. Generally, it's easier to think of acids on the bottoms, but in this case, 14 is at the bottom here. 14 is the most basic or alkaline. So you're going to get your stronger bases. So the higher the number, the stronger the base. The higher the pH, the stronger the base. And just like that, the lower the POH, the stronger the base. And then on the other side, the lower the pH, the stronger the acid. The higher the POH, the stronger the acid. Because if it's a higher POH, it's a lower concentration of hydroxide. And if there's more H plus than OH minus, you're going to have that acid properties. It's all based on the concentrations there. Measuring pH, generally this is pretty easy. It's got the pH reader here. That can be used, or indicators can be used. So there's certain indicators that change color at certain pHs, so they can tell you the pH of a certain substance, depending on the indicator you use. This is just a few examples. So you'll see as something moves from 0 to 2, methyl violet, whatever that indicator is, will change color. And then you got a whole series of indicators here that you can use to show what the pH of your solution is. So section 5, strong acids and bases. Strong acids and bases, this is important, strong acids and bases are known as strong electrolytes. And what a strong electrolyte is that it completely dissociates into its ions. Strong electrolytes completely dissociate into their ions. So HCl, strong acid, completely dissociates into H plus and Cl minus. So it's a strong electrolyte. If you see strong electrolyte, think strong acid or strong base. The most 7 common strong acids include, this is important to memorize, HCl, HBr, HI, HNO3, HClO3, and HClO4. Easiest way to remember that is that HCl or Cl, so chlorine, bromine, iodine, that's all in the same groups. The other two have 2 more oxygens than hydrogen. So HNO3, 2 more oxygens than hydrogen. HClO3, 2 more oxygens than hydrogen. And then as you add on that extra oxygen, it just becomes slightly more acidic. So you'll see that there's no really general rule to remember that. That's just, you got to memorize that. And then H2SO4, again, 2 more oxygens than hydrogens, so it's a strong acid. That's a general rule to remember. If there's 2 more oxygens than hydrogens, it's most likely a strong acid. Unless there's carbons, then it gets a little funky. Nitric acid exemplifies the behavior. Okay. Yada, yada. This is just showing the way that that a strong acid reacts. Remember, they don't form an equilibrium reaction because they completely dissociate. Strong acids do not form equilibriums with just water because they completely dissociate. Remember that. This is just going through the calculations. If something is diprotic, all that means is that it has multiple hydrogens. So what's going to happen is it's going to break down. You know what? We'll actually see that in section 6. So I'm not going to go over that now. Okay, moving on. Strong bases. Again, you just have to memorize these. These are all your group 1s. So you've got NaOH and KOH, both in group 1. And ionic substances from heavier alkaline earths. So that's group 2. So strontium hydroxide. If you remember these solubility rules, strontium, calcium, barium, those are both very soluble. So strontium hydroxide, calcium hydroxide, and barium hydroxide are all strong bases because they can dissociate. Weak acids. This is where it gets a little bit tricky because now we can start looking at the equilibriums, because remember, with strong acids and strong bases, there is no equilibrium. So we're going to still use HA, but instead we're going to have HA dissociate into H plus and A minus, but it's not going to completely dissociate because remember, weak acids do not completely dissociate into their ions. Okay, we can write our equilibrium expressions for this. So you're going to put the products over the reactants. So you got H plus and A minus. Remember, H plus can be also written as H3O plus because H plus and hydronium, they're the same exact thing because the amount of hydrogen ions equals the amount of hydroxide ions. So products over reactants equals Ka, and Ka is just the equilibrium constant of an acid. Ka is the equilibrium constant of an acid. It's just showing what happens with a weak acid. Okay, so which one of these would be the strong acid? It would be the one that has more hydronium ions that are formed. So you see that this one, there is no HA molecules left in the solution because it completely dissociates. In the weak acid, there are HA molecules. There's a lot of them, and there's only a little hydronium ions ion concentration and a little A minus ion concentration. Sounds confusing. All you need to know is that weak acids do not completely dissociate. They don't completely break up into ions, and there's still some of them left after their reaction. And they can form equilibrium equations too, equilibrium reactions. The larger the value of Ka, the stronger the acid. That's important to know. So you'll see all the strong acids that we talked about before. They'll have, they'll have stronger Ka value. They'll have higher Ka value than something like acetic acid or hydrofluoric acid, which are both weak acids. For most weak acids, Ka values range from that. So extremely low Ka values means weak acid. Calculating Ka from pH. Remember that pH is just the negative log of the H plus concentration. So this is where the numbers start to get a little bit difficult. So remember that we can form our equilibriums because we have a weak acid here. So we write out our equilibrium expression. And then we know that pH equals the negative log of the H plus concentration, which is also the product here. So if we know the pH, we know that the negative log of that concentration equals the pH. We can get the log over to get log of the H plus concentration equals the negative 2.38. And then we can solve. And the best way to do this, let me think about the best way. When you're trying to solve logs, it's log base B of A equals C. If you want to take it out of log form, remember B is your base. It helps if you say log base B of A. So B is your base. So you're going to have B raised to the C equals A. B is the base of your exponent C. B is the base, so log base B. B is the base, which is underneath the exponent. B raised to the C equals A. So you can do the same thing here. So you got the log of the H plus concentration equals negative 2.38. So you can rewrite that as 10, because remember, anything that's written as log is assumed to be log base 10. So 10, which is the base, raised to the negative 2.38. Oh, I wrote a 3 there. 2.38 equals the hydronium concentration. Really sloppy there, but I'm trying to keep inside the lines. You get the point. All I'm doing is following the same thing that I did here. That's just a general formula for solving logs. Use that same thing. You can even plug in a variable if you want. Log of x equals negative 2.38. X equals 10 to the negative 2.38, and then just solve that. Use your calculator and solve that. If you're looking for a cheap way to get it, easy way, just remember it. It's 10 raised to the negative pH equals the hydrogen concentration. 10 raised to the negative pH equals the hydrogen concentration. Okay, this can also be solved using ice boxes, which are, again, or you could take this a step further with ice boxes, sorry, not also solve this. Once you have your hydrogen concentration at the end, you can plug that into your ice box, get Ka. That's just all the stuff that we did from equilibrium. So you know that the final hydrogen concentration is going to be 4.2 times 10 to the negative third. That's what we calculated up here. Plug that in, find your changes to be the same exact thing because it's all 1 to 1 to 1 mole ratio. And then you use these numbers in your equilibrium expression. That's just basic equilibrium icebox steps. Okay, moving on. Percent ionization. Percent ionization, this is a big formula to know. Percent ionization equals the concentration of ionized HA over the original concentration of HA. But when it says ionized HA, what does it mean? It means the hydrogen concentration. Because remember, the HA is the acid. It's going to break up into the H plus concentration. So you take the H plus concentration in equilibrium, put it over the original concentration of the acid, times 100. That's how you get your equilibrium. H plus over acid times 100 equals percent ionization. You just plug numbers into that, and that's how you get your percent ionization. For this, that's the constant. This is the concentration of the acid originally. That's the concentration of the H plus. So you do the concentration of the H plus over the concentration of the acid times 100 equals 11. Yeah. These are just all practice problems. Next page. So before we were using pH to calculate Ka, let's use Ka to calculate pH. So it's going to be the same things, just going backwards. So we already got our Ka, 1.8 times 10 to the negative fifth. We can write out our equilibrium expression, which is going to be the products. So these are the products over the reactants. So CH3COOH. Set that equal to the equilibrium constant, so Ka. And then we can take that and we can use our ice boxes to figure out what we can substitute into that equilibrium expression. So we can, for this, see if they, oh, perfect, they got it down here. So we know that since we're starting with 0 here, we're adding X, same mole ratio. So we're also adding X, same mole ratio. So we're subtracting X. Plug these final equilibrium numbers into the equilibrium concentration here using this formula. Set that equal to that, to the Ka. Solve. If X is small enough, you can get rid of it on the bottom, but you cannot get rid of it on the top. Because remember, anytime that you're adding something to 0, the change is just going to be so great that you can't get rid of it. The only time you can get rid of it is when you're adding or subtracting it to a non-zero number, and it's small enough. So solve this using algebra. You find the concentration for X. Remember up here, X is also the concentration of H plus at equilibrium. So we can use that X then as the concentration of H plus. So the concentration of hydrogen at equilibrium is X. So then we can plug that in for pH. Remember, P is negative log, so negative log of the H plus concentration. And then we find our pH. Those are the steps. Then we can go on to do percent ionization. You take the concentration that we found here for H plus, so 2.3 times 10 to the negative third, put it over the original concentration of the acid, so 0.3 molars, times 100. That's just plugging into the formula. This is the 5% rule. Basically, all it's saying is that if X is really, really small, you can get rid of it. It's always a safe bet not to get rid of it, but sometimes it gets difficult. But just make sure after you're done doing your calculations that it is really small and that you could get rid of it. Finally, we compare weak acid. This is just saying that the pH of a strong acid is going to be lower than the pH of a weak acid. We already talked about that. Moving on, polyprotic acid. Remember, polyprotic acids are acids that have more than one hydrogen. So we've got sulfuric acid, I believe that is. Sorry, sulfurous acid. Sulfuric acid is H2SO4. It's going to undergo 2 ionizations because it has 2 hydrogens, but it's not going to do it both in the same step. That's the key to polyprotic acids, is that it doesn't do it in the same step. So the first step, you'll see that it'll get rid of the H+, form HSO3 minus, and that's similar to what the Arrhenius theory said, is where an acid's going to form the H+ and increase the H+ concentration. And then this, the HSO3 minus, is going to go on and shed another hydrogen and form SO3 2 minus. So biggest thing here to know is that the only thing that really matters for pH is the first hydrogen, is this first step here. And you could tell that because of the Ka value. Notice that even though it's not like big, it's big compared to Ka2. So Ka1 is the Ka from the first step, Ka2 is the Ka from the second step. Notice that Ka is so much larger than Ka2. Ka1 is so much larger than Ka2. And when you add the two to get your final Ka, Ka2 is barely going to change Ka1. But you just got to know that polyprotic acids have 2 ionization steps. So it's going to lose the hydrogen twice, and it doesn't happen at the same time. It's 2 separate steps. Again, it's always easier to remove the first polyprotic acid than the second, first proton than the second one. Some more examples. Yeah, just the biggest thing for polyprotic acids is that the first hydrogen is really what gives it the acidic nature, and that the second one barely affects it because it has such a small Ka value. Moving on, weak bases. Okay, many substances behave as weak bases in water. Weak bases react with water, abstract. Okay, weak bases basically act the same as weak acids in terms of like writing equilibrium calculations and things like that. Ammonia is your biggest example of a weak base, NH3. NH4 is an acid, NH3 is a weak base. Ammonia is NH3, ammonium is NH4, so do not get confused by that. Remember, when it's a weak base or a weak acid, we can write the equilibrium equation for that. So instead of Ka here, we're going to use Kb just to show that it's a base. So Kb equals the products. So ammonia is going to react with water to form ammonium plus hydroxide. Water is a liquid, so it's not included in the Kb formula. So you're going to do the products over the reactants. So products, reactants, that's just your regular equilibrium. As with K, okay, so this is just saying that Kb means the equilibrium constant for a base. Kb, base dissociation constant, yeah. Okay. Okay, these are just a few examples of weak bases. Okay, types of weak bases. Weak bases fall into 2 general categories. First is a natural substance. Okay, organic amines. Okay, NH3, again, biggest example of a weak base. You'll see it in action here. See something else like what would this, NCH5, something like that. Anything with an N and an H generally can act like a weak base. That's what this is saying. Just think of NH3 ammonia if you